Okay, powers of a linear function. So basically what we're going to be doing in this one is we're going to be making a generalized formula, or more like a shortcut for whenever you've got a linear function inside a power function. Okay, so again, it's a composite function, but it's just a linear function inside of a power. Now, we're going to start off by generalizing this and showing what the generalized form is. So what we're going to do is we're going to find the derivative of ax plus b all to the power of n. So we're going to start off by letting y be equal to a to the power of ax plus b to the power of n, okay? And just like when we do our composite functions, okay, we're going to let u be equal to the thing on the inside, okay? Now, what we need to find is dy du, okay? And to do so, we're going to do, we're going to find dy dx. We're going to find the derivative. And when we do so, we're going to find dy du times du dx using that chain rule, okay? So I should probably mention as well that this is the chain rule. Dy dx is equal to dy du times du dx. So to do so, I'm going to need to find what du dx is over here, okay? So if u is equal to this, du dx is equal to, well, that's just a, okay? So b disappears. This is x power 1, so 1 comes down and that gets disappeared, so we're left with the a. Okay, remembering that the derivative of a constant function, of a linear function, is just the gradient of that function, so a in this case. Okay, we also know that y is equal to u to the power of n, so then our dy du is equal to, it's going to be the nu to the n minus 1, like that, okay? So putting this all together back over this side, we get dy du is equal to n lots of u to the n minus 1 times, and du dx in this case is just equal to a. So putting this together, we get a n u to the n minus 1, and then resubstituting our u in to get our derivative in respects to x, we're going to get a n lots of, it's going to be ax plus b, all to the power of n minus 1. And so basically, this is the generalized form for the derivative of a linear function. Okay, so essentially what you're doing is you're taking the gradient that's of the linear part, putting it on the outside, okay? You're also taking the power, the original power of the function, so the n, and you're putting it down the front side, outside too, and then you leave everything else the same except you subtract 1 from the power. That's it. Okay? So what we're going to do is we're going to have a look at an example of this happening, and you'll see that it's actually quite easy. So it says, use the standard rule, d dx of ax plus b all to the power of n is equal to an, lots of ax plus b to the power of n minus 1 to differentiate the following linear power. Okay, so if that's y, then dy dx is equal to, okay, so what we're going to do is we need to, so we've got the power out the front already, so I can leave that there. So we're going to take our function, so the numbers on the inside, we're going to take the gradient, and we're going to put that out the front. We're going to take the power and put it out the front as well. Okay. Now we're going to put our function back on the inside, but then subtract 1 from the power. And that's it. That's all we need to do. So 2 times 4 is 8. 8 times 7 is 56. So it's going to be 56 lots of 4x minus 1, all to the power of 6. And that's the whole derivative. Okay. So as you can see, it's much quicker to do it that way, and it's a good little trick to remember. But remember, you can also just do it the long way too, where you let u be equal to 4x minus 1, and then y is equal to 2 lots of u to the power of 7. Okay, so you can do it either way, but this is just a quick trick for those linear functions. This doesn't work for anything other than a linear function, so you can't do it for, say, when you have x squared, or when you've got like some other power of x inside the brackets. It only works when you have a power of 1 on the inside, because we can pick out what that gradient is straight away. So with that being said, that is number 2. In the next video, we're going to be having a look at specific tangents and stuff without actually having to graph these things. So it's always nice. Okay, so we'll do that in the next one.